Hello friends, myself Professor Vinayak Kadam, Associate Professor in Chemistry, PG Department of Chemistry, MSc, Arts Science and Commerce College, Malegaon. Friends, in previous two video lectures, we will discuss the introduction to coordination chemistry. In these two lectures, we will see the basic parts of coordination chemistry. Then, today's important points are difference between the metal complex and metal chelates. Then we will also see the IUPAC nomenclature of coordination compounds. Hello friends, our today's point is difference between metal complex, metal chelates. Second point, nomenclature of coordination compound, and third point is effective atomic number rule. So first we will see the difference between the metal complex and metal chelates. Friends, in metal complex, the monodentate ligands attach to central metal ion. This ligand is called as the complexing ligands. Then, in case of metal chelates, the polydentate ligands form metal chelates, and such ligand is called as the chelating ligands. The second difference point between metal complex is that when monodentate ligands attach to central metal, at that time heterocyclic ring is not formed here. Means these metal complexes are non-cyclic compounds. While in case of heterocyclic metal chelates, a heterocyclic ring is formed, and this cyclic ring is formed by the chelating ligands or polydentate ligands. This is an example of metal complex. Tetramine copper second ion. See here, these ammonia, 4-ammonia, these are the monodentate ligands, and these monodentate ligands attached to copper, this form a complex, and therefore this monodentate ligand ammonia is a complexing agent. When ammonia attached to copper, at that time there is no heterocyclic ring. That's why this is a simple compound or called as a metal complex. While in case of metal chelates, here this is ethylene diamine, second ethylene diamine, this is the bidentate ligands, and this bidentate ligand attached to copper, at that time the cyclic ring is formed. 1, 2, 3, 4, this 4-member cyclic ring is formed. So this ligand is called chelating ligands, and this ring is called a chelate ring, and resulting complex is called as a metal chelates. So this is the difference between the metal complex and metal chelates. So due to non-cyclic compound, there is no ring formation in metal complex, they are moderately stable. If we consider the stability of this metal complex, they are moderately stable. While we consider the stability of metal chelates, the metal chelates are highly stable because in metal chelates there is a formation of cyclic or heterocyclic rings. So this is the difference between the metal complex and metal chelates. So friends, then we will proceed to next point, that is nomenclature of coordination compounds. We call it IUPAC nomenclatures. So there are different types of coordination compounds, and when we naming the coordination compound, there are certain rules, and according to the rules we can write the IUPAC name of any coordination compounds. Therefore, there is a committee, Inorganic Nomenclature Committee of the International Union of Pure and Applied Chemistry, means we call it IUPAC. So according to this IUPAC committee, there are certain rules. So first we'll see the naming of anionic complex. So friends, the complex ions are different: cationic complex ion, anionic complex ion, and non-anionic complex ion. So first we'll see how to write the IUPAC name of anionic complex ions. See here, this is example, put K2PtCl6. In this example, so this PtCl6 is a complex anion and this is a cation. In such types of complex, means anionic complex, at that time when we write the name of this complex anions, so first we can write the name of cation. Then after writing the name of cation, write the full name of anion, and the names of cation and anion are separated by a small space. Means it is written as a two words, first the name of cation, then full name of the anion. See here, in this particular example, K2PtCl6. In this example, this is a potassium, K2, and ionization it gives PtCl6 2 minus. It is anion. So according to this rule, first we write the name of cation. So cation is potassium. So we can write the potassium, then small space, and then write the full name of anion. So in square bracket, this is the 6 chlorine and this is a platinum metal. Therefore, its name is a hexachloroplatinate. And finally, we can write the oxidation state of the central metal in a small bracket in Roman word. So this is a rule, IUPAC rule, nomenclature rule to write the name of complex anions. So when the complex anions are there, at that time, first we consider the name of cation, then full name of anion, between cation and anion name, small space, and then finally we can write the oxidation number of central metal ion in a small bracket with Roman figures or Roman symbols. So second example is this K3FeCN6. Similarly, in this second complex anion, the potassium is a cation and FeCN6 anion. So first we'll write the name of potassium, small space, here potassium, small space between cation and anion, then write the full name of anion. So in square bracket is a FeCN6. Therefore there are 6 cyanide, therefore it is hexacyano. Then metal is iron, it is a ferrate, join the suffix ate, and oxidation state of iron is 3. It is right in Roman word. Therefore, for these two examples, the IUPAC name according to this rule, these two rule is that the potassium hexachloroplatinate 4, and for second complex the potassium hexacyanoferrate 3rd. In this way, the cation is potassium, it is named first, same rule. Anion is in square bracket, there are 6 chlorine, therefore hexachloro. Metal is platinum, it is not free. See here friends, this metal is not free, it is combined with chlorine. Therefore when we write the name of metal, at that time we can't write directly platinum, but we can join the suffix ate at the end of metal. Instead of platinum we can write platinate. Here instead of ferrate we can write, instead of ferrum we can write ferrate, and finally we can write the oxidation number of that metal in a Roman words. So in this way, when we give any complex anion, at that time we can follow this rule to write the IUPAC name of complexes. Then we proceed to second rule. So this is a cationic complex anions. So when the complex is cationic, at that time we write the IUPAC name of this cationic complex with the help of this second rule. So this rule says that the complex is cationic, then containing cationic complex anion and anion, then name of the ligand present in the square bracket are written according to the order given in the rule 5. If there are so many ligands, means 2 or 3 types of ligands, then first write the name of the ligands, write the name of neutral ligands, then name of negative ligands, and finally write the name of the positive ligands. So follow the rule number 5 for this naming the ligands. See here, this is the CONH36Cl3. This is the cationic complex ions. So when we write the name of this cationic complex ions, so first write the name of cation. So here in square bracket, this is a cation, CONH36, this is a cation, and Cl, Cl is anion. So when we write the name of this cation, so in square bracket, first write the name of ligands. So ligands are ammonia. There are 6 ammonia. Therefore, the name is a hexaamine. Central metal is cobalt. So name is hexaamine cobalt. Then write the oxidation number of central metal. Oxidation number of cobalt is 3 in Roman word. And finally write the name of anion, which is outside the square bracket. So second rule says that when the complex is cationic, at that time first write the name of cation, full name, then write the name of anion, and there is small space between cation and anion. So second example is here CrH2O4Cl2. This is in square bracket and Cl outside the square bracket. This is also example of cationic complex ions. When we write the IUPAC name of this complex anion, cationic complex anion, at that time we follow the rules. So first one, we can write the name of negative ligands. So negative ligand is chlorine. There are 2 molecules, therefore its name is a dichloro. Then water ligands, 4 water molecules, therefore its name is a tetraaco. Therefore first write the name of ligands, then central metal atom with their oxidation state in Roman words, and finally write the name of anion. So full complete IUPAC name of this complex is dichloro tetraaco chromium. See here, dichloro tetraaco chromium third. So this third oxidation state, and finally write the name of anion which is outside the square bracket. So in this way we can write the IUPAC name of any cationic complex ions. So such simple tricks to write the cationic complex ions. First write the cation which is inside the square bracket, and then write the name of anion which is outside the square bracket. See here second example again. Here CrH2O4Cl2Cl. In this cationic complex ions, these are the 2 chlorine, then 4 water, and metal is a chromium. So its IUPAC name is dichloro tetraaco chromium third chlorides. So in this way, for some metals we can write their Latin names. Example, copper, its Latin name is cuprum, so we can write cuprate. Iron metal is there, its Latin name is ferrum, we can write ferrate. We join the suffix ate at the end of the Latin name of that metal. Then if the metal is lead, its name is plumbum, we write the plumbates. Metal is gold, its Latin name is aurum, we write aurate. Metal is silver, its Latin name is argentinum, we can write the argentates. Then third rule is the IUPAC rule for non-anionic complex ions, means neutral complex ions. So when the complex is non-anionic, then for non-complex ion we can write the all IUPAC name in one word. There is no space between the cation, anion and the ligands. So when we write the IUPAC name of non-anionic complex, at that time first we can write the name of negative ligands, then the name of neutral ligands, then the name of metal at the end, and valency of metal shown in a small bracket in Roman figures. So when we write the IUPAC name, there is no space between the ligands and the metal. See here, this is the non-anionic complex, means neutral. In this complex there is no charge. So when we write the IUPAC name of this complex, so first we can write the name of negative ligands. In this particular example, negative ligand is chlorine. There are 3 molecules, therefore trichloro. Then neutral ligands is ammonia. Ammonia again 3 molecules. Its name is a triamine. So friends, first we consider when we write the name ammonia is there, ammonia ligand is there in any complex, then we can write the name of ammonia as amine, means V double M is used here. Therefore, particular in this example, the IUPAC name is trichloro triamine cobalt, and small space, then write the oxidation number of metal in a Roman figures. Therefore, complete IUPAC name according to the rules of non-anionic complex ion is that the trichloro triamine cobalt third. In second example, see here. First write the name of negative ligands, then name of neutral ligands, then metal and its oxidation states. See here, the tetrachloro 4 chlorine, diamine 2 ammonia, metal is platinum, here platinum, oxidation number is 4. Therefore, IUPAC name of this complex, non-anionic complex is the tetrachloro diamine platinum 4. So in this way, we will see these 3 rules, one for cationic complex, second for anionic complex, and third for non-anionic complex. Then next rule is the names of ligands. Friends, there are different types of ligands, neutral ligands, positive ligands, and negative ligands. So when we write the name of neutral ligands, then we simply write the name of that neutral ligands. See here, if ethylene diamine is ligand, we simply write the name of ethylene diamine. Ethylene diamine is a neutral ligand. Then triphenyl phosphine is a ligand, we simply write the name triphenyl phosphide. When we write the name of neutral ligand directly, there are again some exceptions. So these exceptions are here. Example, water is there. Water is also neutral ligand. But when water is there, then we can write the name aqua instead of water. In previous example, see here, there are 4 water molecules. We don't write the tetra water. We write the tetra aqua. Means this is exception. When we write the name of water, we can write aqua instead of water. See here, aqua. Then ammonia is there, we can write the amine. And when we write the name amine, we can join the double M. Here 2M is used. And other amines is here C6H5NH2 mixed phenylamine. So when phenylamine is there, then we can write only 1M. Then if NO is there, nitrosyl. CO is there, carbonyl. So these are the names of neutral ligands. Means neutral ligand is present in any cationic, anionic or non-anionic complex. We simply write the name of neutral ligands. Only exception is that in case of water, we can write aqua. In case of ammonia, we can write amine. Then in case of other amine, we join single M. Then NO is there, nitrosyl, CO is there, carbonyl. Then in complexes, negative ligands. So when ligands are negative, then at that time we can join the O at the end of negative ligand. See here, if the ligand is fluorine, we can write fluoro. Ligand is fluorine, we can write chloro. For bromine, bromo. Iodine, iodo. Cyanide, cyano. Then nitrate, nitro. Then nitrite, nitrito. Then nitrate, nitrato. Then amide, amido. In this way. Other negative ligands like oxalate, oxalato. Carbonate, carbonato. Means we simply join O instead of TE at the end of negative ligands. Means any complex, either cationic complex, anionic complex or neutral complex, there is a negative ligands, then we simply join the suffix O at the end of negative ligands. Then positive ligands. The name of positive ligands is present in any complex, then we can join the suffix IUPM at the end of that positive ligands. Example, nitrosyl. If nitrosyl is there, then it is nitronium or nitrosylium. Hydrazine is there, then hydrazinium. Means we write the suffix IUM in case of positive ligands. So when we write the name of neutral ligands, we simply write the names. When the ligands are negative, we join the suffix O. When the ligands are positive, we join the suffix IUM. These are three important rules to write the name of any ligands in either cationic complex, anionic complex or a neutral complex. Then next important rule is a order of listing ligands. I previously explained already this is a fifth rule, order of listing ligands. If the ligands are many in the complex, at that time first we write the name of negative ligands. Means there are 3 or 4 types of ligands. Then first we can write the name of negative ligands, then name of neutral ligands, and finally write the name of positive ligands. It will be simply says negative to this side, neutral at the center, and positive at the last. So after naming the ligands in square bracket, the name of the metal in a square bracket is written with its valence in a small bracket. Remaining rule is same. See here, particular in this example, CONH3,4NO2Cl and ClO4. So this is the complex. So in this complex, when we write the IUPAC name, then first we write the name of negative ligands. So negative ligand is here chlorine and nitro. If 2 negative ligands are there, then we can write the name of negative ligands according to their alphabets. Therefore, according to alphabetical series, chlorine will be first. Therefore, write the name of first chlorine. So chloro, then negative ligand nitro, then neutral ligand is 4, that is ammonia. Therefore, tetraamine. Therefore, chloro, nitro, tetraamine. The name of metal is cobalt. There is oxidation state in Roman word in a small bracket. Oxidation state is 3, and write the name of anion which is outside the square bracket. This is a perchlorate. Therefore, according to the order of listing ligands, this rule we can write the name of different types of ligand. Negative ligand first, then neutral ligands. In this example, there is no positive ligands. Therefore, the name is that chloro, nitro, tetraamine, cobalt, third perchlorates. Here, I already say if there are 2 ligands same, means either 2 positive ligands, 2 negative ligands or 2 neutral ligands, then we can write their name according to alphabetically. I already explained. This is the 5th rule. Then friends, 6th rule, naming the prefix. Naming the prefix under this rule, So some ligands are 2 or 3 numbers, and in the name of that ligand there are again the word di, tri or tetra. At that time we don't write the repeatedly di, tri, tetra. Then we can directly join the prefix. See here, ethylene diamine. In ethylene diamine there is di word, and if the ethylene diamine is 2 molecules, then we don't write diethylene diamine. So instead of repeating di repeatedly, we can join the prefix bis in case of di. If tri is there, then tris. 4 is there, tetrakis. Means we, instead of repeating the word tri, we can write the Greek language bis, tris, tetrakis. So this prefix is used when the ligands having the word di, tri, tetra, and these ligands also having number 2, 3, 4, then we can use this Greek language prefix. See here, in this particular example, so COAN2Cl2Cl. In this example, this ethylene diamine, and this ethylene diamine ligands having 2 molecules. Therefore, diethylene diamine, instead of writing diethylene diamine, we can join the prefix bis for this ethylene diamine. So when we write the IUPAC name, so first write the name of, again, listing of ligands, negative ligands. There are 2 molecules of chlorine, dichloro. Then join the prefix bis because 2 molecules of ethylene diamine. Bis, then in small bracket, name of that ligand. Name of this ligand is En. En is short symbol and its name is ethylene diamine. Therefore, dichloro bis ethylene diamine. The name of metal, it is cobalt, oxidation state 3, and the name of anion, which outside square bracket, chloride. Therefore, according to this naming of prefix, the IUPAC name of this complex is dichloro bis ethylene diamine cobalt chloride. Cobalt third chloride. Then 7th rule is of oxidation states. So oxidation state is written in a Roman word 1, 2, 3 or 0 in a small brackets at the end of the name of the complex without a space between the two. The negative oxidation state minus sign is used before the Roman figures, and 0 is used for 0 oxidation states. Means the oxidation state is 1, we can write the 1 in Roman word. Oxidation state is 2, we can write the 2. Oxidation state is 3, we can write the 3. Oxidation state is 0, we can write the 0. Oxidation state minus 1, we can write the minus 1 before the Roman words in small brackets. So here NaCO4. In this example, the IUPAC name is here, this is the anionic complex. In anionic complex, first we write the name of the cation, sodium, then full name of anion, tetra carbonyl cobaltate. Space between cation and anion, name is cobalt. Cobalt is not free, therefore it is ATE suffix. Then oxidation number of cobalt is -1. Therefore IUPAC name is sodium tetracarbonyl cobaltate -1. Then second example, K4NiCN4. This is also anionic complex. So first write the name of cation. Cation is potassium, small space. Then tetra, cyanide ligand, cyano. Then nickelate. Nickel is not free, therefore nickelate, join suffix ATE. Oxidation state of this complex is 0. We can write the 0 in a small brackets. In this way, we can write the oxidation number, oxidation state of central metal ion. Then point of attachments. Unit entity ligand has within itself more than 1 or 2 donor atoms. In ligands, there are 1 or more donor atoms. Sometimes, example in thiocyanates, nitrogen is donor or sulfur is donor. Means which atom is attached to central metal, then write the symbol of that donor atom after the name of that ligand. This is the point of attachment. See here, this is an example. Its name is ammonium hexathiocyanate N chromate third. Means in this particular complex, the nitrogen is a donor. Therefore, we can write the nitrogen symbol after the name of these ligands. So, its name is ammonium hexa isothiocyanato N chromates. Then second example, ammonium isothiocyanato chromate third. Means here in isothiocyanato, this sulfur is a donor atoms. Therefore, here nitrogen, carbon and sulfur in thiocyanate, 3 atoms are donor. Then which donor atoms are attached to metal? At that time, we can write the donor atom symbol after the name of that ligand. This is the point of attachments. See here, in this example, ammonium hexathiocyanato yes platinate 4. Means in this example, the sulfur is donor. Ammonium hexathiocyanato sulfur platinate 4. Here nitrogen is donor, here sulfur is donor. Therefore, we can write the name sulfur symbol. Here we can write this symbol of nitrogens. If the complex sulfur acts as donor, so we can write the symbol S after the hyphen after the name of ligands. Hexa isothiocyanato sulfur. Then in this examples here, potassium dithiosulfato. So here potassium dithiosulfato means here one ligand is a sulfate, but this is sulfur atom, this is the oxygen atom. Therefore, we write both the symbol sulfur and oxygen here. So potassium is a cation, this is the name of anion. Potassium small space 2 sulfate, therefore dithiosulfato. Oxygen sulfur platinate, oxidation state is a second. In second example, the oxygens are donor. Both the donor atoms are oxygen. 2 molecules of thiosulfate, but oxygen is a donor. Here 2 molecules of thiosulfate, but 1 oxygen and 1 sulfur donor. Therefore, we join the suffix. We write the suffix. We write the symbol oxygen and sulfur. In second example, potassium dithiosulfato, oxygen oxygen. This is symbol oxygen oxygen small hyphen platinate second. So in the case of nitrate ions, nitrogen or oxygen is a donor. Therefore, if nitrogen is donor, nitro. Oxygen is donor, then nitrito. Then ninth rule is the abbreviations. Some ligand possesses long and complicated name. So when we write the name of these ligands, then we write the small abbreviation, that is EN, PN, PY like this. EN means ethylene diamine, PN means penanthroline, PY means pyridine, EDTA means ethylene diamine tetraacetic acid. Friends, we will see these abbreviations in last video lecture when we see the types of ligands. There are different types of ligands, particularly polydentate ligand, bidentate ligand, tridentate ligands. Then we write the small name there. EN means ethylene diamine, PN means penanthroline, PY means pyridine, EDTA means ethylene diamine tetraacetic acid, OX means oxalato, like this. Means these are the small abbreviations is used when we write the name of the ligands having a very large name. Then bridging groups. Next rule is a bridging groups. So the ligands that bridge two metals. Suppose particular ligands it bridge two metal. OH ligand bridge to these two iron metal. At that time, the polynuclear complex are bridged by the Greek letter mu. At that time, we write the symbol mu before the name of bridging ligands. It is repeated before the name each different kind of bridging groups. The resulting complex is called the bridge complex. So ligand which can join two metal atoms from a bridge, this complex is called as the bridge complex. See here, IUPAC name of this complex is mu dihydroxo. So these are the two hydroxo groups which form the bridge between these two metal. That's why mu dihydroxo. Octa-echo means there are 8 water molecules. Octa-echo di-iron, and oxidation state is the third, and sulfate is outside the square bracket. So in this way, when we write the bridge ligand's name, at that time we write the suffix or Greek letter mu before the name of the bridging ligands or bridging groups. Here second complex, these are the two bridge ligands both the ligands are different. One is NH2 and second is NO2. So when we write the IUPAC name of this complex, then mu amido, this is a bridge ligand from a bridge between cobalt. Then mu nitro, this nitro from a bridge between these two cobalt. So IUPAC name of this complex is mu amido, mu nitro. Then octamine means there are 8 ammonia. Octamine 2 cobalt, dicobalt, oxidation state 3, and this is nitrate outside the square brackets. So IUPAC name of this bridge complex is a mu amido, mu nitro, octamine, dicobalt, third nitrates. Also called as octamine. First write the name of negative neutral ligands. Octamine, then mu amido, mu nitro, dicobalt, third nitroamine, and the same. Then friends, next rule is the 11th rule, geometrical isomers. So in the coordination compound or complexes, there are two types of complexes, cis and trans complexes. So we already see cis and trans isomers or cis and trans complexes. So cis means similar groups or adjacent signs, means 90 degree away. Positions, and the term trans means opposite sides, means 180 degree away. So the number for cis and trans is that in square planar complex 1,3 group and 2,4 groups are trans positions here. So this is 1,3 group, 1 number and 3 number. Similar groups to 1 and 3 position, 2 and 4 position, then this complex is called as a trans complex. Or similar groups at 2, 3 position or 1, 4 position, it is called as a cis. Means 90 degree away is called as the cis isomers and 180 degree away is called as a trans isomers. So this is name, IUPAC name is that. So in this complex, these are the two ammonia. So both the ammonia is the same groups, and same groups 180 degree away, or these same groups at position 2 and position 4. That's why this complex is a trans chloro nitro diamine platinum second. So IUPAC name, geometrical isomers, IUPAC name of this complex is a trans chloro nitro diamine. So first write the name of nucleative ligands, then neutral ligands, then platinum metal means central metal with their oxidation states. Therefore IUPAC name according to this rule is that chloro nitro trans chloro nitro diamine platinum second. Then in this complex, here 1 chloro, all groups are different. Therefore 1 chloro, 3 nitro, bromo amine platinum 4 ion, bromo amine platinum 4 ion. Then octahedral complexes, in octahedral complexes 1,6 position is called as a trans positions, and 2,4 position is also called trans position, and 5,3 position is also called as a trans position. Means 1,6 position, 2,4 position, and 3,4 position is called as a trans position. See example in case of octahedral complex. This is one example. Here in this complex, 1 chloro, 2 bromo, 4 iodo, 6 nitro, amine, pyridine, platinum 4. So this is a complex having different groups. But here these similar groups to adjacent position, these similar groups to adjacent position, therefore the cis isomers. So IUPAC name of this complex is cis dibromo. So cis dibromo tetramine, these are the 4 ammonia, tetramine rhodium third, or 2,3 dibromo tetramine rhodium third. Means at 2 and 3 position identical groups. This is the cis isomers. So this is the rules to write the IUPAC name of geometrical isomers. Then friends, next rule, optical isomers. So there are two types of isomers, dextrorotatory and levorotatory. When the isomer is dextrorotatory, then we write the symbol plus, and isomer is levorotatory, we write the symbol minus. So dextro complex also represented by D symbol, levo complex also represented by L symbol, small d or small a. So this is the rules to write the suffix plus or D, minus or L for optical isomers. So here potassium plus or D trioxylatoroiridate third. This IUPAC name of any optical isomers. Then next rule is the 13th rule. It is for chelating ligands or multi-dentate ligands or chelating ligands. See here, in this complex COEN2SO4. In this complex, the ethylene diamine is ligand, and therefore this ethylene diamine again having the di word. Therefore, IUPAC name of this complex is bis ethylene diamine small bracket copper second sulfates. So when ethylene diamine occupies two coordination positions, other molecules have capacity to attach central atom at even more than two positions. Therefore, these are the two molecules, and therefore this ligand is called as the multi-dentate ligands or chelating ligands. Resultant complex is called as a chelate complex. There is a ring formation. So this ethylene amine form a ring between these two nitrogen. This ethylene diamine form a ring between these two nitrogen, and therefore this complex is called the chelate complex. So in this way, friends, with the help of these 14 rules, we can write the IUPAC name of any complexes. These are some examples here for homeworks, and we can write the IUPAC name of any complex. Suppose we see this example. So according to our rules, so this complex is a cationic because here positive charge. This is a cationic complex. When the complex is cationic, then first write the name of ligands. When there are different types of ligands, then write the first name of negative ligands, then neutral ligands, then name of metal atom with their oxidation state. So when we write the IUPAC name according to cationic complex, we can follow the rules, and according to the rules, the IUPAC name of this complex is a dichloro-2-chlorine tetraamine. Here ammonia is ligand, double M in their spelling, double M. So dichloro tetraamine. Metal is cobalt. Oxidation state is 3. Ion. So IUPAC name is a dichloro tetraamine cobalt third ion. So in this way, we can write the IUPAC name of any complexes. These are the all examples. See here, particularly this example again. In this example, this is also the cationic complex. So chloro, nitro, tetraamine, cobalt, third perchlorates. Then this complex. See here, in this complex, the ethylene diamine 3 molecules. Therefore, when we write the IUPAC name, this is again cationic complex. So when we write the name of cationic complex, first we can write the name of ligands. So ligand ethylene diamine, there are 3 molecules. Therefore, join the prefix tris. 3 molecule tris. Then in small bracket, its name En means ethylene diamine. This small abbreviation En. En means ethylene diamine. Its number is 3. Therefore, tris ethylene diamine. Metal is chromium. Their oxidation state is 3. And this is the name of anion, which is outside the square bracket. Therefore, according to IUPAC nomenclature, the IUPAC name of this complex is a tris ethylene diamine chromium third chloride. See here, this is one example. This is a DMZ. DMZ means dimethyl glycoxime. So in dimethyl glycoxime, the word is di. And again, this dimethyl glycoxime 2 molecule means dimethyl diglycoxime. Di word is repeated. Instead of write the repeat, we write the suffix bis. Bis means 2 molecules of DMZ. So when we write the IUPAC name, then its name is a bis. DMZ means dimethyl glycoxime and nickel second. So in this way, we can write the IUPAC name of these examples. This is the all examples given. With using above rules, we can write the IUPAC name of any complex. Thank you, friends.